Can you hear
Yes,
me?
I can hear you. Who is it?
It's Savannah Morel.
Yes, okay. Yes, I saw your name pop up, but I couldn't tell if you could hear me yet or not.
Yeah,
Uh,
I couldn't hear you. I was trying to fix my audio over here as well.
right. Once I get these slides up, I can't see anymore, okay, who's here. So let me go through real quickly and let you know who I marked as present. And let me know if anyone else is at it. I've got Andrea, DeAndre, Tamika, Madison, Savannah, Addison.
Here.
Yeah, I've got you. Addison, T, Jamal, both Rachels, and Alyssa. Is there anyone whose name I did not call?
Leah Johnson.
Who is that?
Leah Johnson.
Oh. Yeah, there you are. Z, right?
Yes.
All right. Anyone else whose name I didn't call? Okay. Now, y'all can see the names pop up better than I can. I don't know why. It's just that I guess I'm the host and I've got all these other things open. So when you see someone else come on, let me know they're here. Okay? Right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 people logged in right now that I know of. Myself would be the 13th. I don't know if you see that or not. But let me know if you see anyone else pop up, and we'll try to get them, because sometimes they can't hear or maybe can't talk, one or the other. So we'll go from there. All right, it's been a week since we met, and a lot has happened in that week. Let me go over just a little bit of what some of those things are. Did all of you realize we are not going back to campus this spring? Is that a surprise? Is that a surprise to anybody?
No.
No. Okay. They decided this over the weekend. The chancellor said, well, the governor said K-12 wouldn't be going back for the rest of the spring. It would all be online. And then the chancellor said the same thing would be true of our system. And then our president came on and said, yep, we'll be continuing. This is called virtual classroom or virtual classes, when we meet at a fixed time and we communicate with each other like we're doing now. In the future, when you see them talking about things, this is a virtual class. Online class is, even though this is online, an online class is different. An online class, the instructor puts out the material, the student picks it up anytime they can, does the work, resubmits and stuff like this. They may have chat rooms and things like this, but basically there's no fixed class like we have. That's called online instruction. This is what we're calling virtual instruction. We're in a virtual classroom. We're a virtual class. We meet together at a fixed time and have class together. So we're doing that the rest of the spring. The other big news that came out of it was summer is also not going to be on campus. Summer will also be virtual, with a few classes that are online, but most of the classes will be virtual. So and the summer schedule, they're having to change it all now to reflect that, and we'll be, as soon as this class is over, I'll be meeting with the dean and associate dean in a Zoom session just like this, and we're going over the math schedule and possibly also some of the physical science. And then hopefully that'll be published by the end of the week. So if you are planning to come this summer, it's going to be just like we're doing now, unless you're in an online class, which will then be strictly online. You won't necessarily meet with the instructor like we're doing now. So there is a distinction being made between online and virtual. This kind of a setup is virtual. Right now I'm fiddling with my power cord because it doesn't always plug in well, and doesn't look like I have a blue light where the power should be, but it is faint, but it's there. Okay, sorry about that. Now, another bit of news, I guess. The college is doing everything it can to set up all the support, everything done like we normally do when we're on campus is now going to be done virtually. If you need to communicate, say with the records office, they have an email address now that's just records, RECORDS with an S on it, at lawsonstate.edu. The business office has an email address that's business office, no space, no underlines or anything else, just business office at lawsonstate.edu. And several of the other offices probably will have or have now something like that, so you can communicate with anyone there. Now, a few of the places will be on campus occasionally. That's just because they have to go in and take care of some things they can't do at home. Okay? But don't count on anyone being on campus. If you need to go to campus, like if you left something on campus that you're going to need before the spring is over, contact campus security on whichever campus it is and let them know that you need to pick up something, and they will probably let them know when you can do it. They will probably arrange to have someone meet you, open the doors, let you in. We're practicing social distancing, so even if you see someone on campus, stay that 6 feet apart. Even the campus security, stay 6 feet apart and get things taken care of. And my suggestion to you would be, as soon as you're back in your car, use your alcohol wipes or whatever you got, hand sanitizers. Make sure that you're keeping yourself safe. I'm sure y'all are having to do that at work as well. Okay, and it was good to hear that at least some of you still have work to do. Madison, said she was at work some, and that's why she'd missed some classes. So I'm glad some of you got jobs. Other people don't. So glad that some of you are able to maintain a job, but it's somewhat difficult in this environment. Okay, also I posted on, okay, here's another deal. Are all of you able to access the Blackboard message system? Do you know what I'm...
Sent the test.
Okay. When I started off this process, I started putting these announcements on announcements because that's where I thought they went. And then either someone told me about it or I landed on it myself and found that little envelope up there at the top, and that was messages. And when I opened that, I found out students have been sending me messages. So I thought, oh, this is how they respond to announcements, so this must be how I make announcements. So I thought it was just a shortcut. So I started doing everything on messaging. Then this week, I've learned that not everybody can get or send messages. Specifically, one guy this morning had an iPad, and for some reason his iPad would not show that little envelope, so he could not access and never got any word on the message. So last night I had started, because I had heard a complaint about that the day before, on yesterday, so I started sending them both ways, but now I found out some people can't even see or access messaging. So from now on, I'm going to send everything that I send to you via announcements, because I think everyone can get that. And if you want to send me stuff back by messaging, I'll still be checking messaging. I just won't be sending by message. For instance, the last test, the test for Chapter 16, I sent last night via a message. Did all of you receive that? If you didn't, it may be that you're not getting your messages. I'll have to send that again by announcement. So let me know. Did y'all all get that?
I got it.
Did anyone fail to get the test for chapter? It's called Test 4, Chapter 16 test.
I'm going to have to check and see.
Okay. Yeah, and Madison, I thought in your email it sounded like you hadn't gotten it. Did you find it? I'm not sure Madison got connected voice-wise or audio-wise because I couldn't hear her before. I just saw her name pop up. Well, anyway, any further questions? Any uncertainties? Any clarifications you need? Okay, if not, and if you have missed some classes, they're all out there on YouTube videos. As you see right down here in the corner, I am recording. Okay, so in fact, I just noticed my pen is still red, so let me change it to black. All right, I have to change it every time we change screens. So if there are no more questions, then let's hit the topic 6.5, resonance. Okay, now everything pretty much has what they call a natural frequency. Natural frequency. Natural frequency of an object, and they use as a tuning fork. I guess you've seen those. The picture on the next page, page 443, shows a tuning fork, someone hitting a tuning fork. If you've ever watched anyone tune a piano or something like that, you've probably seen one of these. They make a really pure noise, okay? They vibrate at a very specific frequency, and that's called the natural frequency of that device, okay? That's the frequency at which it vibrates okay, when struck by another object, like that tuning fork on the next page. My pen is really strange. It's late in the day. It doesn't act very well. When struck by another object. It's not writing well at all. That was an O that didn't complete itself. Okay. Such as a rubber hammer or something like that. Now, a few examples of this, and there's one coming up. In fact, that picture that you saw of the tuning fork on page 443, if you got your books open, you see that hitting one, and if it's in located on a box that sort of sends the signal across to another one, if that other one's on the same frequency, it will start vibrating without touching it. And that's because you're hitting the natural frequency. Right below that, you see the picture of a singing wine glass. Okay? I remember seeing this and having people do it. I've done it myself. Now, usually you need a pretty nice quality of glass. Sometimes regular glasses don't do this too well, and that's why they show wine glasses. They're usually very thin glass and usually a very uniform glass, you know. And you can dip your finger in water and rub your finger around the rim, and it will start making a louder and louder noise. That's because it's on its own resonant frequency, and it's reinforcing itself. There was a dumb movie, I think it was Miss Congeniality, with Sandra Bullock. I don't know if you saw that. She was supposedly the Miss USA pageant or something like that, was under threat, but they didn't want to panic people, and so they entered her. She was an FBI agent. They entered her in it, and they had to get her to act like a beauty queen, even though that wasn't her natural way. And so her talent was going to be playing a song on singing wine glasses. She had it all set up, and the other girls in the pageant were thirsty, and they started drinking. They didn't know the water was not for them. So anyway, it was a dumb story. But anyway, that does set up. The more you fill the glass, the higher the frequency. The less water in the glass, the lower the frequency. So that's why you can set up different notes with that. Something else that's probably a little more common, I know that probably most of you have pushed somebody in a swing. And of course, when you push someone in a swing, you don't push on them when they're on their way up to you. You wait until it stops, and then you push, and they go further the next time. That's because you're getting on the natural frequency of that swing. If you try to push when they're on the way up, everything falls apart. They may even fall out of the swing because you've broken the natural frequency of the swing. I don't know if you've ever pushed off a car before, but if you have, of course you put the car in neutral, and someone's usually sitting in the car with their foot on the clutch if you had a clutch. If it's automatic, they're in neutral, and you push on the car. If you can get it rocking just a little bit, you don't keep pushing, you push, let it come back to you, and right when it starts to go back again, push again. And every time, right when it starts moving on its own, rocking on its own, that's when you push, and after a while, you can move the car, sometimes all by yourself, because you're getting on the natural frequency of that car. Okay? That's the resonant frequency. So those are probably more examples than you cared about. That's the natural frequency, and on the next page they mention the term resonance. So resonance occurs, and again my pen's not writing, and I don't know why. Okay, resonance occurs when the natural frequency natural vibration rates of two objects are the same. Okay. Now here's another. I don't know if you've ever heard this before. Have you ever, either you yourself or heard someone call into a talk radio show? And almost always they'll say, turn down your volume, okay, on your radio if you're listening to that. Because, and here's why, if you don't do that, you hear, screeching. What's happening there is your voice is being picked up by the microphone again, in the telephone, on your computer, whatever it is, and it's the same frequency as your voice. So it's adding to itself, and soon it sounds like it's about to explode with noise. And that's why they tell people to turn off the radio or turn down the radio so they can talk on the telephone and call in show. It happens with Zoom too. Just about every time the dean, I have a session with the dean, I'm hard of hearing. There's something about the frequency of her voice, when it goes through the computer, I can hardly hear a word she says or make them out. I can hear she's talking, but I can't make out more than about half the words. Especially if multiple people are on, it seems like it cuts down on her volume. So what she has me do, she calls me on my phone, and then I'm talking on the phone to her. Well, what happens is it starts echoing, and they get louder and louder because my phone's picking up my voice that's coming back on the system. And, I have to either turn off something on the phone or turn it off. I turn it off on my computer screen so it doesn't pick that up. So those are all examples of resonance. Okay. If you have some fairly good quality crystal glass at home, put some water in it, run your finger around like they show in that picture. You'll see that happening. Okay. That's all they do on resonance. until the end of the chapter. And I'm pretty sure, yes, the end of the chapter there'll be another picture, and it's an amazing picture of what can happen with resonant frequencies. You may not think it's very important, but it can be. Now, I don't know in your sonography course if you ever will run into the situation where something just isn't working well because the sound is getting too much. You may want to change frequency. Somehow you may be on some other object's resonant frequency. So that's all for 16.6. There's no problems. There's no formulas. They're just telling you about that because it is a pretty important thing. So let's move to 16. That was 16.5, resonance. 16.6 is simple harmonic motion. Okay, I guess I'll continue on this page. So simple harmonic motion. I'll spell it out one time here, if the pen would write. Okay. Now from now on, now the pen's not writing. Look at what it did with my M there. And it does this, and I do not know why. Okay. Okay. That's supposed to be simple harmonic motion. The pen is just really weird. From now on, I'm going to call this SHM, simple harmonic motion, so I don't have to write all those letters because the pen's not doing a good job with it. It's a type of linear motion I don't know why the pen's so lagging, okay. Linear motion, though we'll see an example that doesn't seem to be linear, but it sort of is, okay. In which, and this is sort of a technical definition, in which the acceleration, there again the pen is screwing up, okay. Sometimes I'll be writing something, pick up the pen and go somewhere else, and then the screen connects the dots, and that's what just happened there. In which the acceleration okay, of the object is directly, this is pretty technical, proportional okay, left off the R, still won't write the R there, directly proportional to the displacement see, it's not writing at all, or it's lagging really slow. From the equilibrium position. Okay. The motion is always directed toward the equilibrium position. My pen is doing such strange things now. It's not writing and I can't see. Okay. Toward the equilibrium position. Okay, I'm going to quit writing. Okay. Now, I wish that this figure was there. So I'm going to have to ask you to picture this. In fact, I'll draw it. Does anyone need a little more time to get that down? Can I erase the screen? Any objections? Take that to be none. Okay. I hope I haven't lost everybody. Okay. Here is sort of the classic example of simple harmonic motion. A spring. Okay. A spring with a mass on it. Okay. Now, we're going to fiddle with that some. One thing we're going to do is stretch that spring. Okay. Another thing we could do is compress the spring. Okay. Now, the pen didn't draw my circles there. Okay. That's pretty ugly anyway. When the spring is in equilibrium position, let's just call this the equilibrium position, everything's happy. If you don't mess with it, it just sits there. It hangs there at that position fine. However, if you were to pull down on that mass, like the second picture here is, then you'll feel the spring pulling back on you. And that's why they said it's a type of linear motion in which the acceleration, and when you see acceleration, think force. When the force on the object is directly proportional to the displacement from the equilibrium position. If you pull that mass just a little ways from the equilibrium position, the spring's pulling back just very slightly. But if you pull harder, it's going to pull back harder, because that's what springs do. Okay? Now, also, if you were to compress the spring, push it against the spring, you'll feel it's pushing back toward you. The further you push, the stronger the push is back. The force or the acceleration is directly proportional to its displacement from the equilibrium position. Is that making sense? Now, let's think about if we did stretch this, like we say there in the second picture, stretch it out, holding it down there. You're having to hold it against the force of the spring trying to pull back. If you were to release that, then the spring's going to pull the mass up this way very strongly. It's starting from initial velocity of 0 because you are holding it there. So when you release it, the force is pretty great upward. It's going to accelerate upward, and as long and until it gets to that equilibrium position, the spring is still pulling on it, adding more force, adding more acceleration, so it's going to be picking up speed. So when it gets to the equilibrium position, it's not going to stop because it's now at its maximum speed, and its inertia, remember that from an earlier chapter, keeps it going up until it compresses the spring. And it's going to keep compressing the spring until the force of the spring down equals, and that's proportional to how much it compresses, stops it and then starts pushing it down again. So now it starts moving downward once it's compressed. But guess what? The further it was from the equilibrium position, the more it's pushing down. As long as it's above that, it's pushing down more, accelerating more. When it passes the equilibrium position, it's going at its maximum speed again. And then once it passes it, the spring starts pulling up and starts slowing it down again. So what do you have? You have a mass that starts down here and goes up here and goes down here and goes up here and goes up here. That's called simple harmonic motion. It keeps going back and forth. The speed is minimum here, okay, because it's got 0 here and here. Maximum here, that's the speed. The force is maximum here and here because the spring's pushing or pulling in the opposite direction. So the force is maximum here and here. But the force here is 0 because that's at its equilibrium position. It doesn't want it to leave, but the trouble is it's got so much speed, it's going to keep going. So this is the velocity is the max there. Does that make any sense? If you've ever played with a spring, you'll know it does that kind of thing. You pull down and release it, and it goes up and down and up and down. Now, it doesn't do it forever because there's a certain amount of friction within the spring, and it does dampen itself out. Now, have any of you ever ridden in a car that had really bad shock absorbers? You may not even know what the shock absorbers are, but does anyone know what I'm talking about? I think I put you all to sleep, or you've all gone home. No, you are home. Okay, whatever. Okay? What I mean by that is the shock absorbers are the things that dampen that motion. And in doing so, they stop it from going back and forth. Well, if your shock absorbers are shot, not working, then that spring just has you going up and down and up and down and up and down, and that's a very miserable way to ride. Okay? So anyway, that's an example of simple harmonic motion. Now, remember some of the terms that we had for waves back at the beginning of the chapter? The same terms we deal with here. Okay? The displacement of an object is how far above or below the equilibrium position it is. This one is displaced this way. This one's displaced that way. Okay? I haven't drawn them evenly, but they're displacement. How far it is from the equilibrium or rest position. And equilibrium and rest position mean the same. That's from there. I don't know if you can read that. I'm going to say rest position because it's easier to write. That's the displacement. Okay? Now, the maximum magnitude of the displacement and we've heard this word before, that's the amplitude. We talked about the amplitude of a wave, the maximum above or below the equilibrium position. The amplitude of the vibration is the maximum displacement, which is above or below. Now, I'm going to get out of this slide for right now. I'll be coming back to it because I'm going to go to this slide. Now, this doesn't look like linear motion, does it? This is a Ferris wheel. But what's linear about it is you consider this. Let me get my pen back. I can't get it back. There we go. We consider this to be the equilibrium position. Okay? Now, how they're picturing this is what if you're the only one on the ride, the only one in a chair, okay? Sun's directly overhead, and you're looking at the shadow down here. When you're either up here or down here, the equilibrium position, your shadow's directly right there, okay? And then as you turn this way, your shadow moves this way, and once it reaches the maximum over here, then the shadow starts going back here, passes equilibrium position, and goes back to this maximum, okay? So here would go the shadow, back and forth, simple harmonic motion. There's the linear motion. Yeah, you're going in circular motion around the Ferris wheel, but your shadow is going back and forth in equilibrium, in simple harmonic motion. So the simple harmonic motion of the shadow of the person is shown on the line PQ, and that's what I just drew over. You can't see very well, so I'll erase all that. That is your shadow right here, going back and forth from one side to the other, where the person is rotating at a uniform speed on a circle of a Ferris wheel. When the person is at the position A, there he is, right there, okay, or she is, right there, that's where you're A prime, okay? And then B prime or when you're at B, just past the equilibrium position. C prime is, your shadow is right at the maximum. That's going to be the amplitude there, maximum displacement. D will be, the shadow will be at D prime, and E is back here at, well, just beyond where you are there, okay? All right, they correspond to those positions. So that shadow would be going simple harmonic motion. So it doesn't have to be a spring or anything like a spring. Lots of things follow simple harmonic motion. Now, when I say the word harmonic, what do you think of? Anything special? Harmony. Any of you sing? When you talk about singing, we say people sing in harmony, meaning they get on similar frequencies of their voice, or frequencies of their voice that match each other well, okay? Say one may be alto, one soprano, but going with notes that are in the same range there, you know. So, that's exactly what we're talking about. Music is simple harmonic motion. The vibration of your larynx in your voice, simple harmonic motion, okay? If you think about daylight and darkness hours, they go back and forth, maximum daylight, maximum darkness, back and forth, simple harmonic motion. The earth moving around the sun, simple harmonic motion. Just about everything physically, you run into simple harmonic motion just about everywhere. So we mentioned amplitude, the maximum displacement that an object can have from the equilibrium position. Remember that term period? What was the period? Period. The symbol for it was capital T, standing for time. The time it takes for you to go through one complete cycle. That's the period. Like if you started here, let's start here at C prime. You're right on the edge here. The time it takes for you to go all the way to Q and then all the way back to P, that's one period. That's the time. Time, seconds per cycle. You could think of it that way. It's measured in seconds. Okay? And on the other hand, what was reciprocal of period? Anyone remember? One of the F words. Frequency. I can't write well with this pen. That is little f usually, and that's measured in per seconds, or cycles per second. 1 over second. Another way is 1 over second. And see, that's a reciprocal of your time, of your period, is the frequency. The number of complete vibrations per unit time. Where the period is the time for one complete cycle, the frequency is the number of cycles per unit time. So one is time per cycle, the other is cycle per, how many cycles per time. All right. Simple harmonic motion also can be represented by sine or cosine waves. The amplitude is how far above the equilibrium position it is. The frequency is what time it takes it to go make one complete cycle. The frequency is how many cycles it makes in one time period. Not period, but time. So therefore, sine waves are great ways to represent, or cosine waves, by the way, but either one. One other device that mimics this, and I think that's the last slide we've got. So I think I'll go back to the other, my clean page. Okay. Let me get there. and go from current slide and get my pen back. Okay. Is a pendulum. Okay. Pendulum is sort of a bob that hangs down from either a rod or a string or a cord or something like that. And what you do with this, you raise it over here and let it go back and forth. Anyone think of anything when you see a picture like that? A grandfather clock, right? The pendulum on a clock. And that's why it keeps time so well, because it's a fixed time for its period. And if you fix the length of the cord so that it does in exactly 1 second, then every time it goes, it's going to advance 1 second or 2 seconds or whatever your period is. Okay? So this is called a pendulum. Okay? An object suspended so it swings freely back and forth. Okay? I won't write all that down. There it is. Okay? They're used in clocks for keeping time. Now, of course, you have to wind the clock. Why? There's always friction loss. Always friction loss. Whatever your gears or things in the clock, there's always a little bit of friction loss. Just the fact you hear a tick, 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 that means something's producing sound. You also have air resistance that is always trying to oppose the motion of the pendulum. So that's why you have to wind the clock, because it won't keep going forever. Okay? The closest it comes is in that box. If you think of your grandfather clock or grandmother clock, they have a smaller version. And think that pendulum at the end is a big circular thing most of the time, but it's big that way. But if you look on the edge, it's very thin edgewise. That's to cut down on air resistance because it's swinging back and forth. You want a mass there, but you don't want a lot of resistance. So they make it big, circular big in 2 dimensions, but in the 3rd dimension, the direction it's going, very, very thin. They usually also enclose it in a box, right? Usually a glass box so you can see, but that enclosed in the box so you cut down on air movement that would slow it down or possibly speed it up, usually slowing it down. So that's why they minimize that. There are 3 basic properties of a pendulum that was discovered by good old Galileo. And here is the first property he discovered. Its period that is your T, remember, is independent of the mass. It really doesn't matter how much mass you have on the end of that. Usually they're pretty good size, but they don't have to be all that heavy. You want enough so it doesn't get influenced too badly by wind resistance. Okay? A very light object, think of a ping pong ball, you can blow it and it blows it off your hand. That wouldn't be a good mass to have. Something that's heavier than that. Okay? So independent of the mass, because air resistance is more affected by the size. I would say it the different way. The motion would be more affected by air resistance by the size and shape of the body than its mass. Okay. Okay. Number 2. Second thing that Galileo discovered. Its period is also independent of the amplitude. Okay? Now, we were given, I think it was a wedding gift, but maybe it wasn't, maybe a few years after, or very soon after we were married, may have been a Christmas gift. It wasn't a grandfather clock, but a grandmother clock, a lot smaller, but it had a pendulum. Okay? The amplitude is how far you lifted that from the equilibrium position to get it to float, to going. I would always lift it as far as I could till it hit the glass on the side and release it, and it would come down to its normal frequency. It didn't need to go that high. It would get down to the length it wanted to be and just go back and forth. So it was independent of the amplitude. I didn't have to raise it up that high, but I didn't know how high to raise it, so I just raised it that high. Okay? So it's independent of its amplitude. That's as long as the arc is small. And if you think about it, those boxes are pretty narrow, so you can't raise it too far. As long as the arc is small, it's independent of, that is less than 10 degrees. Okay? The third thing. Well, what in the world does the period depend on? Subject to those conditions, a small arc, all these kinds of things, the period T is equal to 2 pi. Boy, anything that acts like it's going in a circle, seems like pi always shows up, times the square root of the length of it over the acceleration due to gravity. Remember that from earlier chapters? G was 9.8 meters per second squared, or 9.80 I think it was, or 32.2 feet per second squared. Well, this is the length. That's what determines the period, not anything else. Not the mass at the bottom, not how far you lifted it, as long as you stayed less than 10 degrees. It's the length. That's what matters. And that's how we could adjust our grandmother clock. Had a little screw thing that you could lift or lower the some threads, like a little nut that would lift and lower the pendulum bob, the mass at the bottom, to try to lengthen or shorten the length of the pendulum. The trouble is the clock always, I'm trying to remember now, it hasn't worked in several years, it always ran either a little fast or a little slow, and I adjusted that as far as I could and never could get it to get just right. It always was just one way or another, no matter how far I turned it, that wasn't far enough to get rid of it because I ran out of threads. So there is the formula for the period of a clock, usually in seconds. Okay? 2 pi, no units associated. Those are just numbers. 2 is a number, pi is a number. Pi is 3.14159. It's an irrational number, never repeats itself, never ends. So that's why they just call it pi, so I don't have to write all those digits down. This is the length. Now that length could be in meters or it could be in feet, either one. If the length is in meters, then we use G in meters per second squared. If it's in feet, we use G in feet per second squared. Now sometimes, for instance, that grandmother's clock, that length was nowhere close to a meter. So you could use centimeters, but then you change your unit down here from 9.80 meters per second squared to 980 centimeters per second squared. So you have to, if you change your length, you have to adjust your G factor to the correct units. Now notice what happens here. If you divide meters by meters per second squared, the meters go out and you're left with 1 over second squared. No, 1 over a 1 over second squared, which when you invert and multiply, that becomes second squared over 1, which of course is second squared. Take the square root of that and you got seconds. That's what your period is measured in, seconds. Same thing with feet and feet per second squared. The feet cancel out and 1 over second squared is the same as second squared. Take the square root of that and you get seconds. So that's how the units work so well. Okay, any questions on that so far? There is one example on page 446, and by the way, at the top of the page before we get to there it is, try this activity, swing set physics. A swing often serves as a good pendulum, okay? And you can measure the period of the swing as it moves back and forth. Vary the amplitude and or the mass of the person sitting on the swing and check it, and you see the period. Only thing that changes it if you change the length of the swing's chain. Otherwise, it doesn't matter whether you have a heavy person or a light person. Might be harder to push them or whatever, but the period's going to be the same. If you have, what was the other issue there? Push from a real high height or a very small height, the period's going to be the same. Okay? But that's the amplitude. But if you change the length of the chain, then yes, the period changes. So let's do example 1. So I think I will go to a clean page to do it. Remember our formula. We're going to be writing it down very soon. Any questions before I change this? Okay. Find the length. So we're looking for L. Now this will be in centimeters. That's sort of unusual, but in centimeters, of a pendulum with a period. The period is T of 1.50 seconds. Okay? 1.50 seconds. That means every 2 swings will take 3 seconds. So 20 full swings would be 60 seconds or 1 minute. So that would be set up in a gear ratio to do that. Okay? Now, since the length is in centimeters, which G do we use? Anyone want to make a guess? 9.80 or 32.2? Well, neither one of them are in centimeters, but the 9.80 is in meters, and that's the same thing. So we'll use 9.80 meters per second squared. All right. Now, at this point, I would change the G. Not changing its value, you might say, but changing its units. Because we want length in centimeters. Well, okay. Let's write down what the formula is, by the way. What is the formula? We just had it on the slide. Anyone get it? Okay, I can't tell if you're even there. I assume someone's still there. T is equal to 2 pi times the square root of the length over G. See, everything on the right-hand side is a constant except the length. That could vary. 2 is a constant, pi is a constant, and G anywhere on the surface of the earth is a constant. Okay? T would then be measured in seconds. So that's the independent variable is the length, the dependent is the time, or the period. However, this is asking for it in a different thing. They're asking for the length. So what we need to do is isolate the L. Now, how can we do that? Anyone have any ideas? I don't know if everyone's muted their phones or what. I can't hear a thing. I guess you want me to do all the talking. What's that? I can't hear. Huh? Someone said something, but I couldn't make it out. Let's first divide both sides by 2 pi. That's legal. Okay, so you got rid of that. Now, next obstacle here from isolating the L is that square root sign. How do we undo a square root? Anyone have a clue? Yeah, raise it to a power of 2. Square this side, square this side. Okay? So that, the square and the square root basically undo each other. So that's getting a little messy, so I'm going to write it down what we've got now. L over G is equal to the period over 2 pi squared. That's what we got, right? We're wanting to isolate the L. What do? One last step. Any idea? Isolate the L. Multiply both sides by G. Excellent. That gets rid of the G's on this side and gets it over there. Now, since we're looking for L in centimeters, this is what I was going to say earlier. Let's go on and change this G to centimeters per second squared. So I'm going to multiply by a conversion factor to give me something in centimeters per second squared. Now notice we're not changing the seconds. We're only changing the centimeter. So you tell me what unit we'll put above the line, what unit below the line. We're changing meters to centimeters. That's all we're changing. One goes above, one goes below. One of them's meters, one of them's centimeters. Which goes where? Okay, I hope I heard centimeters on top, meters on the bottom. That way the meters will cancel out and you're left with centimeters right where you want them. So now the question is, how many centimeters in a meter or how many meters in a centimeter? Anyone know that one? Okay. Now, millimeters would be 1,000. Centimeter, think of cents in a dollar. How many cents are in a dollar? 100. So it's a cent is a centidollar, 100th of a dollar. So 100 centimeters are in 1 meter. Okay? I'll come back. Okay. Now, we've got it. 100 times 9.80 would be 980 centimeters per second squared. Okay? So, that's why I'll do it. The book does it slightly differently. I think this is the easier way to do it. Okay? We know the T is 1.50 seconds. Okay? We know 2 pi is just 2 pi. Okay? We're going to square that quantity and multiply it by G in this units, which is 9. I'm so used to doing that. 980. I can't get my pen to erase. Okay, 980. What's that? 980 centimeters per second squared. All right. Now, that's before we do too much. This is going to be our L. That's what we've solved for, L. I can't get the L to write. There we go. We wrote 3 times it. Okay? This line didn't. Okay? When we square this seconds here, we're going to wind up with a second squared. That cancels that second squared out. So we're going to wind up with centimeters. That's exactly what we wanted the answer in. So let's do the math. If you've got your calculators, I happen to have mine today. I may be slower than you. I probably am. Okay. All right. The calculator will do, I still don't have it. Okay. Now, what I'm going to do, I'm going to square everything by itself. Okay. So I'm going to do 1.5, I have to turn my calculator, squared, times 980, that's not squared. Then I'm going to divide that by 2 squared is 4, so divide that by 4, and then divide that answer by pi squared. So I'm going to enter the pi and then square it, and then press equal. Okay, does anyone get an answer? I got 55.9. And I think that's what the book got as well. 55.9 centimeters. The units per centimeter. Now what the book did, they kept everything in meters per second squared, and then at the end they converted the meters to centimeters. You could do it that way, that's perfectly fine. You just wound up with a pretty small number for the meters, but that works just as well. Okay. Any questions on that? All right. That finishes 16.6. There's some problems there at the end. You could do any of the odd ones, 1 through 13, that you can find in the back of the book. I think they're all there. So do some of those. And then for the whole chapter, you have a glossary here. I don't know if you need all those words, especially since any of them that refer to sound waves, they may be important to you later. So I would pay attention to these more than you would most chapters. Okay? Your formulas there, again, are pretty important, especially those that refer to sound. Like 16.3 definitely refers to sound. I don't know if you'll be doing much Doppler shifting. You might. That would be 16.4. Doubt if you'll do much with periods and lengths of pendulum, because I don't think that's what you deal with. But there's that one. Your frequency, 16.1, and velocity, those are probably pretty important too. The 16.2 only refers to electromagnetic frequencies and wavelengths, because the speed of light, that's what electromagnetic radiation does. Your review questions there are good conceptual questions, so it's not a bad idea to look through those, but your problems at the end, that's what your test questions are going to be closest to, any of the odds there, 1 through 17. Now, what I saved till the end was this picture on page 450. I don't know how many of you have your books. This is an incredible picture. Now, this was taken, not a great picture. I think this happened back in 1940. Okay? So way before my time even. Don't be laughing. Okay? They had built this bridge. It was called the Tacoma Narrows Bridge across Puget Sound in Washington. That's not too far from Seattle. The airport in Seattle is called the Seattle-Tacoma Airport. That's the Tacoma they're talking about here. It's a town just south of Seattle. Seattle's the big one. Tacoma's smaller, but they share the airport. It's called SeaTac. Okay? So anyway, they built this bridge across that sound, that bay that's there near Seattle. Big, massive, beautiful bridge. But if you've ever been on the West Coast, you know the wind blows always coming off the Pacific. It's a steady, always blowing, usually in one direction. Very consistent. Well, this bridge, once they had it built, when people would be driving over it, they noticed that it felt like it was swinging, and it shouldn't have been swinging. They called it Galloping Gertie. I don't know where they got Gertie from. It just, alliterative with gallop, because it felt like it was moving underneath them. Well, the wind picked up speed, a certain speed, and was blowing very consistently at that speed for a long period of time, and the bridge started rocking, bigger and bigger waves on it. It tore itself apart. Why? it was on the natural frequency, the resonant frequency of the wind that day. In that fairly long period of time, it was consistently there. It had been moving earlier when the wind was close to that frequency. When it got on that frequency and continued for a long period of time, boy, that thing started rocking so badly it tore itself apart. There were some cars on the bridge at the time. They went into the bay. Okay? Pretty bad stuff. And that's a true story. The civil engineers that designed that bridge never thought about resonant frequencies, obviously. To this day, every bridge built, they measure the prevailing winds, they determine the resonant frequency, and they make sure they're nowhere close to it with their bridges. Okay. Dumb story, but true. All right, what I'm going to do now is get out of this slide for now. Any questions before I do? Now that did finish chapter 16. That was your test 4. I hope all of you got it. Has anyone joined the class who did not get their test 4? I sent it last night, shortly after I sent the YouTube video announcement. Okay? I'm not the YouTube video, the Zoom announcement. It was probably 15-20 minutes after that. Okay? So I hope that you got it. And someone was concerned about the due date. I found out that Blackboard just puts any date that wants to in there, and they put it like the same day or something like that. So I moved it to 2 weeks from today. That's a good target, but don't sweat it. If you need another week, take another week. And since you're sending it back to me online, you're not turning it in on a Wednesday anyway. Whenever you can get it done, send it to me. Okay? But try to get it done in 2 weeks if possible. But that gives you at least 1 week to ask questions if there's anything you can't understand. All right. So I'm going to discard this if no one needs it any longer. Okay. And I'm going to go to this other one. Now I'm going to have to knock you offline for a little bit. Not offline, you'll still hear me. But I have to close this one out. And then I need to pick up. I don't think I can do it from here. I'll take a little bit. Okay, here we go. Go to my computer and the movable disk. And, oh, I could have gone here. Let me close this. I had it already here. I hope I closed the right thing. Go here. This is where I want. And we're doing now to chapter 17. It's coming up slowly. Okay, here we go. We'll get it from current slide. And I'll go back to Zoom. And I need to pick up my share again. New share. And this will now be chapter 17 PowerPoint. Okay. And we'll go from current slide. All right, my question to you now is, can everyone see that slide? Chapter 17, basic electricity.
Yes.
Okay, you got it back. Good. Sorry, that took a little time. Okay, going through all these different programs, it's not easy. Okay, this begins the chapter with the next to the last test. Now, we got 2 more chapters, but one chapter has just a couple sections in it. The other one only has 1 or 2 sections in it that we're covering. So those 2 will be on the last test. But chapter 17 will be its own test. Chapter 18 and 19 are combined, because there's not that much we're going to cover out of those. But this is next to the last test that we have will be this one on basic electricity. Okay? Now, let's start with the concept of electric charges. What do we mean by an electric charge. As happened in many things, electrification was first studied about 2,500 years ago, 2.5 millennia ago in ancient Greece. It was found that when you took an amber rod and rubbed it with a wool cloth, the rod attracted small objects, okay, like pieces of paper or dust or things like that. And they found out when any two objects are rubbed, sometimes they become charged. Okay? They didn't know why. And they certainly didn't know what to do with it. Okay? Now, later, and this has happened to me before, when I've worn some fairly comfortable shoes when I was out in the field doing work, when I worked at Southern Research Institute, we did radon research down in Florida, and we usually stayed at some pretty cheap motels, just because we're trying to save money for the project and not spend it all on motel stay, okay? So they would have usually polyester rugs or carpet down on the hallways, and usually I was wearing fairly comfortable shoes like tennis shoes or something like that because we were working out in the field, okay? So when you have a rubberized base like that on something like polyester, then I would sometimes pick up a charge. When I would reach for my doorknob, it would shock me because the doorknob was metal and the motel was built with a metal frame. It would shock me. You may have had the same experience if you slid across a car seat with either cotton or wool clothes on, and the car seat was probably not leather but something like a plastic, and reached for the doorknob and you got shocked there. Yes, what you were dealing with was charges, electric charges. And again, that's what we call static electricity. Okay? Now what these charges are, and this is a little involved, but it's not too bad. There are things in the, and before I get going on it too much, I need to go back and remind myself which sections we are going to study here. I'm sure we're going to study the first one, but I don't want to go over things that we don't. Yeah, it's the whole chapter. No, it isn't. It's basically, the main ones are 17, 3, 4, and 5, 7, 8, and 9. So I probably shouldn't spend too much time with this, so I'll just hit it lightly here. What we're dealing with here, this is supposedly a neutral atom. Now what they've drawn here happens to be lithium. It doesn't matter what the atom is. I know it's lithium because lithium contains, let me get my pen back. Okay, is someone saying something? Okay. Lithium contains 3 protons. Now it also contains some neutrons. They didn't put the neutrons in there. The center of this is called the nucleus. In the nucleus lives protons and neutrons. Protons are positively charged. Neutrons are neutral. No charge at all. So that's what lives in the nucleus. Now they've drawn these way out of scale here because the nucleus is incredibly tiny but has enormous mass, because these are, for their size, they're very massive particles, but they're incredibly tiny too, packed into a nucleus. All the mass of that atom is in that nucleus. Flying around out here at great distances are what we call electrons. The electrons always fly around because they're negatively charged. They're attracted to the nucleus, but they don't collide with it. They fly around in what we call orbits around those, or shells around those. They call it the electron shell. They go around their paths there. Now, this is what we call a normal atom, a neutral atom. Same number of protons as you have electrons. They have the same amount of charge, only different signs. Okay? Now, one of the people we attribute this to, Benjamin Franklin, believe it or not, the guy who was the first Postmaster General of the United States, the guy who helped write the Declaration of Independence, the guy who invented the Franklin stove, the guy, he did so many things, okay? He first referred to electric charges as either being positive or negative. He knew they were different. How do we describe them? Well, let's call them positive and negative. To this day, it stuck. The sad news is he named them backwards from what we like to use, but that stuck too. So the protons are positive, the electrons are negative. Okay. Now, if you were to rub this atom, lithium atom, with a certain material, let's say a wool cloth, you might steal one of those electrons. That outer electron really isn't being held very carefully. So if you do that, now this is still lithium. It doesn't ever change the number of protons in the nucleus. That doesn't change unless you have a nuclear reaction, and hopefully we're not going to have any of those, okay? But it's lost an electron. So now we call this a positive charge. Because the electrons were negative, you lost one, now you have a net positive charge. 3 plus, 2 minus, that leaves you a plus 1 charge. So that's called a positive ion. The term here is I-O-N, ion. It's like an atom, but now it is charged. This one happens to be positively charged. Now over here we have another lithium atom, and this is not likely to happen. And these are positive charges in the nucleus, the protons. My pen won't write. There we go. And these are negative charges on the electrons. Now, again, I say this particular situation will not occur, okay? But what happens here, it picked up an electron. So now it's a negative ion. No longer a neutral atom, but a negative ion. Negative because it has an extra electron. So when you have a positive ion, it's never, ever, ever that it picked up an extra proton. You don't mess with the nucleus. Don't mess with Mother Nature. Leave that alone. It's only picking up or losing electrons. Now remember I said the protons and the neutrons are fairly massive, so all your mass is concentrated there. The electrons are so incredibly tiny in mass. Even though they have the same charge as a proton, their mass is like 1/10,000th of the mass of a proton. It's just incredibly small. So most of everything is really nothing, because in between those electrons and protons is nothing but outer space. I mean, it's inner space, but it's just, there's nothing in there at all. All the mass is concentrated in that nucleus, which has protons and neutrons in it, and all the volume is occupied by these tiny little electrons that have almost no mass at all. So that's your introduction to charge, okay? Now I think what we'll do is move on to, we're going to skip induction, that's 17.2, and we'll go to 17.3, that's where we pick up next. So this is all induction, we're not going to worry with this. I've done it before and it takes so much time to do, and you're not responsible for it anyway. So let's skip that. Again, electric induction, that's 17.2. Again, electric induction, 17.2. More slides in this section than any other one, and we're not even doing it. Okay? And there's 17.2 again. These kids, this is called the Van de Graaff generator, and when kids put their hands on it, their hair stands up, because they're all getting the same charge, and the hair, like charges, and this is something you should know from back before. Like charges repel each other, unlike charges attract each other. That's why the electrons go around the nucleus, because those unlike charges are attracting each other. Now what's a mystery is why the protons can live so close together in that tiny little nucleus and not blow themselves apart. That's because there's what they call nuclear forces that are holding them in place that are way stronger than electromagnetic forces, which is what we have here, electric forces. Okay. Now, I think we're at the place where we're beginning this. But in Coulomb's law, there are absolutely no slides. And that's 17.3. In 17.4, there are absolutely no slides. In 17.5, we finally get to the next slide. So the one section we skipped had slide after slide after slide. And now the sections we're going to do have no slides at all. So we'll come back to this if we have time to get to that slide. What we'll do now is go to and why have I lost? There we go. We'll go from current slide here. All right. Can you all see that slide?
Yes.
Yes. Okay. The blank white slide. Okay. So, the charge on a proton is denoted by the symbol, and I kind of don't like this symbology, but it's the one the book uses, and why that shrunk, I don't know. Go back to current slide. Oh, this is open twice. No! This is driving me nuts here. Now I just closed out. Now I've got to go find that slide again. Sorry about this, folks. Hang on, I'll be right back with you. I mean, y'all still see me and everything. We don't want to pause. I want to minimize. I want to minimize. Here we go. I want to move myself. Y'all probably can't see that, but I'm in my way. I'll move myself over here. Okay. And get this one open again. Late in the day, the computer just does whatever it wants to, it seems like. I've still got to do a meeting on Zoom with the dean tonight and the associate dean, and I can guarantee you it's going to cut up because it's cutting up right now. It's been on all day long. I can't get any indication I've got getting power to my computer at all. Hopefully it's not going to go dead on me. Well, okay. All right. Let's go back to Zoom. Y'all still there, I hope, right? Okay, meeting still in progress. Return to the meeting. I need a new share here. And we're going to use this PowerPoint. I've been wondering what this whiteboard is. I wonder if something I can use, but I'll try to figure that out later. I want this PowerPoint. Okay, there we got it. Can everyone, again, we had it before and it just decided to close itself. Are you still there?
Yes.
Okay, can you see the whiteboard?
Yes.
Good.
Yes.
Okay. So, the charge on a proton is denoted by, let me get my pen set up now. Okay. The charge on a proton I like to call a proton a P+. Okay? Now my pen is writing really badly here. P+. What this book calls it is E+. And there is a reason for that. Okay? E is one electron charge. But an electron has a negative charge. Well, the charge on a proton is the same charge, only it's positive. So they use the term E+. I prefer P+ because it reminds me it's a proton, but that's what they use. The charge on a proton is E+. Charge on an electron, and I call an electron an E-, and that is E-. Okay? So the charge on a proton is E+, charge on an electron is E-. Okay? Now, In the study of electricity, a much larger unit of charge is required because no one has the equipment that you can measure the charge on a single electron. That is just so incredibly tiny. There is no equipment built by man that can measure the charge on a single electron. So we have to have some bigger unit that we can actually measure. That unit is called the coulomb. C-O-U-L-O-M-B. Named after a guy named Charles Coulomb. He was born in France, and he pioneers research in electricity magnetism, and they named the unit for charge after him. Because his name was Coulomb, the symbol for it is capital C. Now, if you have been in other science courses, you might say, wait, didn't they use capital C for degrees Celsius in temperature? You'd be absolutely right, because that was named after Anders Celsius. But the difference is, whenever you use C for temperature, you always have a degree symbol. So that's a degree Celsius. This is a coulomb. If it doesn't have a degree sign, it means coulomb. If it does have a degree sign, it means Celsius. We're not going to be using this at all, so don't worry about that. So the unit of charge is a coulomb, capital C, named after Charles Coulomb. Now, the measurement of that for a proton, E plus, the charge on a proton, is given by, and that's a very small charge, 1.60 times 10 to the minus 19 coulombs. That is an incredibly small amount of charge.
Mr. Fowler.
Yes.
Someone has a question.
Okay, what's the question?
What page are you on?
Oh, I'm sorry. We're on 17.3 is the section number, chapter 17, basic electricity, section 17.3 on page 455, right at the bottom of the page. And what we did in this chapter, we hadn't been doing it in other chapters. I just gave you a little bit of information from 17.1, and then we skipped 17.2, and now we're on 17.3, which is on page 455. Great question. Sorry, I should have been saying that. Everybody on the same page? Okay? Now, as I said, that's an incredibly small number. Now, there is something else, since we have a timeout here. We're having work done on our driveway. We had a huge, probably more than 120-year-old tree that back when it was raining so much, the ground was so wet, it couldn't hold the tree in place. It just laid down one evening. I mean, just laid down. No wind to speak of. It was growing toward the sun, so it was leaning to the south, and suddenly its weight got too much for the ground to hold because the ground was so wet, and it laid down. And when it did, some of the roots, massive roots, some of the size of trees, tore up our driveway. Not badly, but a little bit. So we're having the driveway repaired. Is that noise in the background bothering anybody? Anybody? Okay, you didn't even hear it. Well, good. I'm hearing a little bit, but I'm hard of hearing, so I thought it might be bothering some people. So anyway, how small is this number? Okay. If you were to put a 0 here and a decimal point, you would need to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 1, 6, 0 coulombs. That's a pretty small number, wouldn't you say? No scale in the world can measure that small a number, okay? It wouldn't be a weight scale. any kind of scale can measure a number with that many zeros in front of it. So that's why we use coulombs rather than electron charges, because they are incredibly, incredibly tiny. Okay? So what that means is it takes about 6.25 times 10 to the 18 electrons or protons, they're saying electrons now, to make 1 coulomb. Because remember, electron is how much charge that electron has. Now that is an incredibly big number. That would be 6,250, 000, 000. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now I don't even know how to read that number. That would be thousands, that would be millions, that would be billions, that would be trillions. This would be quadrillions, and this would be quintillions or something like that. 6 quintillion, 255 quadrillion electrons to make 1 coulomb of charge. That's an incredibly large number. So when you're combing your hair with a rubberized comb, and if it's dry weather, your hair is pretty clean and that kind of stuff, and then you reach down and pick up a little piece of paper, you have moved a whole bunch of electrons off your hair onto the comb, and that's what makes it charged. Okay? So what we're getting at here is that these are reciprocal numbers of each other. 1 over the 1.60 times 10 to the minus 19 is equal to the 6.25 times 10 to the positive 18. They're reciprocal of each other. If someone has a calculator and want to play around with it, you'll see that if you take 1 and divide it by that number, you're going to get some number very close to that one. Okay. Now, when Coulomb was doing his study, he found out that the charge strength decreases by the square of the distance you are from that charge. That's called an inverse square law. Now, this isn't super important here, but it does have a little bit of play. Inverse square law. Let me give you another sort of dumb example of this. My wife loves to read. And sometimes at night when she can't go to sleep, she'll pull out her Kindle, most of the time a Kindle, and she has a little light that attaches to it, just like you would use on a book too, and that gives her enough light to read. Okay? I sleep through everything, so I don't even know this, but I know she does it because she's sometimes reading when I go to bed. Okay? Now, if she were to take that little light that she had hanging on her Kindle, just right there on top of it, and hang it from the ceiling, would that be enough for her to read with? Nowhere close. Because light also decreases by the square of the distance. So if you increase that distance from a few inches like it was on her Kindle to several feet to the ceiling, then no, there's not going to be enough light for you to read. So that's the same thing here. The charge, the force, the strength of that charge falls off by an inverse square law. Okay? Now, there was one other thing. Remember that picture that I showed of the kids with their hair standing up? That machine, I named it, was a Van de Graaff generator. And what I found totally fascinating, and I did not know this before I read this book, that Robert Van de Graaff, who developed that machine that people use all over the world, was born, guess where? Tuscaloosa, Alabama. I'd never heard that before I saw this book. I thought he was Dutch or something like that, but he was born in Tuscaloosa, Alabama. We're not doing it, but that was interesting enough to say. Okay. The inverse square law behavior was found to apply in much weaker Gravitational force, studied in chapter 5. We didn't do that chapter. It also does with light. It does with electricity. Lots of things follow the inverse square law. Now, why did we even mention that? Well, what we're getting to is Coulomb's law of electrostatics. All right to erase this? Okay, I hope so. Here is Coulomb's law. I'm just going to call it Coulomb's law. One of the basic laws of physics, especially with relating to electricity. Here's how it goes. The force between 2 point charges what we mean by point charges, you imagine all the charges are located at a single point at the middle of that object. 2 point charges, I'm abbreviating like crazy, and by the way, the symbol for charge in this chapter, and usually always, is little q. Q1 will be one charge, Q2 the second charge. The force between those 2 point charges, Q1 and Q2, is directly proportional to the product of the charges and they say here, and this is actually the better way to phrase it, their magnitudes. Now, why would they say magnitude rather than charge? The charges usually have a sign associated with it. All we're looking at is the force between them, and it's the magnitude. Don't worry about the sign. You can deal with that later. So the magnitude, so if it was an electron, you don't worry that it's a negative charge. You just use the magnitude. If it's a proton, you don't worry it's a positive charge. Just use the magnitude, which is positive, by the way. Okay, the product of their magnitudes and inversely proportional to the square of the distance between them. There's the inverse square law. That's the reason we mentioned it. That's Coulomb's law, or the Coulomb's law of electrostatics. This is describing a force, so how we write this down, the force. Now, remember back when we said F sub W was weight and F sub this and so, I like to call this F sub E for electric force, electrostatic force, okay? Now, the book doesn't. They just say F. So I guess that's fine. I think I like to still keep it F sub E, okay? Now that's equal to, now when we say proportional to, that means it's not equal to, but if one goes up, the other goes up, or if one goes down, the other goes up, whatever, that's what a proportionality is. So you have to make it an equal sign. We use a proportionality constant, and that they called K. And even though Coulomb was French, they used K because the German word for constant starts with a K. Okay? The product directly proportional to the product of the charges, or the magnitude of the charges, Q1 times Q2, and inversely proportional to the square of the distance in between. There's the equation. If you didn't have the K, you would say it was proportional to that. But if you put the K in there, now that makes it an equation. And we can deal with equations. Proportionality is hard to do calculations with. Now, it turns out that K is the same no matter what. It is a constant of nature. So the F is the force of attraction or repulsion. So this is force, and it can be positive or negative, meaning positive meaning pulling toward each other, negative pushing apart. What determines that? If the charges are different charges, they pull together. If they're like charges, they push apart. Okay, so that's why we leave the sign off. We determine the sign by whether they're same sign or different signs. Okay, the K here is a constant of nature, and this is 9.00 times 10 to the 9th Newton meter squared per Coulomb squared. That's a rather weird, it's a big number, but it's rather weird units. Well, of course it has to be, because the force is measured in newtons, so you got to have a newton over here somewhere, though that's where it is, in the constant. But you got two charges here, which are measured in Coulomb and Coulomb, so these two charges cancel out those two, the Coulomb squared. And then you're dividing by meters. The radius is measured in meters, and this is meter squared here. So sure enough, you're left just with the unit Newton, and that's what your force is. So there is Newton's, oh goodness gracious, Coulomb's force of electrostatics. Okay? And this is often called Coulomb's constant, by the way. This book, I noticed, doesn't call it that. They call it Coulomb's law, but they call it electrostatic constant, which is fine. Now, they have a little activity here. They say you can try. If you want to, you certainly can. They say, turn on a very thin stream of water, very, very thin, not dripping, but very thin stream of water. Charge a plastic rod, a latex balloon, or anything like that. Plastic comb. Comb your hair with the plastic comb if your hair is fairly clean and it got low humidity that day. But anyway, or just do it with a piece of wool. That would be even better than trying to comb your hair. Okay, or fur if you have some real fur, not artificial. Okay, that would work too. I don't think my dog's fur would work because she's not clean. She's oily. Okay, but anyway, bring that charged object toward the stream of water, and either the stream of water is going to go toward it or go away from it, depending on the charge that the object had. So that's an example of Coulomb's law of electrostatic attraction, or repulsion, by the way. So I think we're ready for example 1. Are y'all ready for example 1? Oh, I can hear the cheering in the background. Okay, all right to erase this? I hope so. Two charges, each with a magnitude of 6.50 microcoulombs. So Q1 is 6.50 microcoulombs. Now, does anyone remember what the prefix micro stands for? It's a millionth of a coulomb. And remember, a million represents 6 decimal places, like $1,000,000. $1,000 would be 3 zeros, $1,000,000 would be 6 zeros. So this would be written without the symbol 6.50 times 10 to the minus 6, because it's a millionth of a coulomb, 10 to the minus 6 coulomb. Well, that's also charge 2, because it says both charges equal magnitude of 6.50 microcoulombs, which is 6.50 times 10 to the minus 6 coulombs. Now that doesn't sound like a lot of charge because it's such a small number, but remember that's quite a few number of electrons. That would only be a few trillion electrons. Okay. Separated by a distance, and that's what in the formula we called R, is the distance of 0.200 centimeters. So that's pretty close together. Okay. Remember, a centimeter is about the width of your little fingernail. So this would be about 1/5 of the width of your little fingernail. So it's not a very large separation distance. Okay. But again, Coulomb's law deals with meters, not centimeters. So we need to figure out how many meters this is. So let's multiply this by our conversion factor and come out with how many meters that is. What unit's going to go where? Second line there is for the units. One goes on top, one goes on bottom. Which goes where?
Centimeters on bottom.
Centimeters on the bottom, perfect, and meters on top. Now you match the numbers with the units. How many meters in a centimeter or how many centimeters in a meter? We had it earlier. Anyone remember?
100 centimeters.
100 centimeters is 1 meter. Centi meaning 100, like a cent is 100th of a dollar. Okay, so what's that going to do to this number? That's going to move the decimal places 2 more digits to the left. So this will be 0.02 0.00 meters. Because when you divide by 100, you move the decimal 2 places to the left. Okay, pretty small number. Okay, but the other one's even smaller. Okay, find the force of repulsion because they have equal magnitude of plus 6.50 microcoulombs. So what's that formula for force? Electrostatic force. Anyone remember? It was just one slide ago. It was K Q1 Q2 over R squared.
I thought if you move the decimal 2 places to the left, it's 0.00 and the 2.
Okay. No, okay. I moved one here, one there, and then put a 0 in front of it. So the decimal. You're right. You're absolutely right. I'm sorry. Good catch there. I thought that looked like too small a number. I was thinking it was a 2.00. Nope, I got too many now. Sorry. Let me start this over. Okay. 0.002. You're absolutely right there. Because another way to think of this, a tenth of a centimeter is a millimeter. That's about the thickness of a dime. So this is 2 dimes next to each other. So 2 millimeters would be 2 thousandths of a meter. So you're absolutely right. Good catch. Okay. There's your formula. What's the K? Remember that? 9.00. It's a big number times 10 to the 9th, isn't it? Easy kind of to remember because both of the numbers in there are 9s with some zeros. Okay, and the units of that would be Newton meter squared per coulomb squared. Now that should be a capital C. I just was writing small. Okay, times 6.50 times 10 to the minus 6 coulombs times 6.50 times 10 to the minus 6 coulombs, all divided by, now do you want to leave that as a decimal number or write it in scientific notation? I really don't care. Anyone got a preference? You're going to enter it in the calculator anyway. I'll just leave it alone. 0.00200 meters squared. When you do that, it'll get even more zeros in it. But if you just do this as listed here, I think you'll come out okay. So, you remember how to use scientific notation on your calculator. Do not ever do a times 10. What you do is 9. You don't need to put the 0.00, just 9 EE or EXP. Now I have a iPhone. Let me tell you what mine says. I'm pretty sure it's EE, but let me get it. Have to turn it sideways. You see, if you got an iPhone, if that's what you're using. If you got a calculator, look for either EE or EXP. On this iPhone, it's the EE just to the left of the 1. Do you see that? Capital E, capital E. It's not that little e. That little e is another number, not electron, okay? That EE, that means your exponent, okay? So it's 9 EE and then 9, okay? Whoops, it didn't show up. Whoops, mine's not doing right. Maybe it did right after all. 9 EE, okay. It was doing it, I just didn't realize it. Let's clear that out of the way. 9 EE 9. That's 9 million, no, 9 trillion, by the way. No, 9 billion, by the way. Times 6.5, you don't need the extra 0 if you don't want to. And again, EE, don't ever do times 10, it's EE. And then on my calculator, I do the 6 and then do a change sign, that plus minus sign. Okay? Then that's times another 6.5 EE, 6, change signs, and I'm going to press an equal, okay? I'm then going to divide that by 0.002, but I'm going to square that number, so I go over there and find my square key, square that number, and then press equal. And what do you get? You might be surprised at how big it is. On my screen, it says 95,062.5. And that would be, is that what you got?
Yes.
Okay. All right. And you see the meter square cancel out, the Coulomb square cancels out, and you're left with newtons. Now your book takes this decimal and moves it 1, 2, 3, 4 places to the right. They make it 9.5, and since that is a 6 there, that's going to round this up to a 1. 9.51 times 10 to the 4th newtons. Man, that's a big force. 95,000 newtons of force. Why is it so big? Even though these are tiny, tiny little charges, millions of a Coulomb in charge, they're really close together. And electrostatic forces are pretty strong. So that's why they got 9.51 times 10 to the 4th newtons. Did everybody get that? Any problems? It's hard to see what you're doing from here, but we can try to do it if you want to talk our way through it. Everybody okay with it? By the way, that is the one and only problem in section 17.3. So, homework exercises here would be any of the odd problems 1 through 7 that are in the back of the book. That is your assignment in 17.3. All right, ready to move on to 17.4? 17.4 is, does anyone need this a little bit longer? Okay. 17.4 is talking about electric fields. And if you go back, 17.3 was Coulomb's law, but what we're dealing with there was electric forces. Now, electric fields and electric forces are very, very closely tied together. Okay? Now, I don't know if you even know what we're talking about with a field. Okay? Let me give you one example of this that all of us are familiar with. We all live in a gravitational field. That means if we jump up or jump off of something, gravity is going to pull us downward. Now, we don't see gravity. We don't know where it's coming from. It's there. It is a force that's pulling without anything obvious pushing on us, okay? We fall down, okay? That's what a field is. A field is a force acting over a distance without, it's not like you're hitting a ball with a tennis racket. No, you know what force that is, the tennis racket hitting on the ball. This is no physical contact, it's just pulling on you. That's what a field is. So we're talking about electric fields. And so far we've discussed electrification in terms of the brushing of electrons from a surface, but in terms of static electricity, an electric field, and I'm going to write this one down, that's not a great definition, but it will work. An electric field exists where an electric force, I said they were related, and that could be attraction or repulsion, either way, acts on a charge abbreviating like crazy, brought into the area. Okay. Now, this is not going to be a great illustration. If we were in class together, I'd be standing around holding up my hands, doing things, you know how I usually song and dance around. Can't do that here. So let me try to draw it here. What if you have some charges here? You want these charges to be positive or negative? You choose.
Positive.
Positive. So here we got a bunch of positive charges here. Okay, we don't know how many, just a bunch of positive charges. Okay? Now, over here we're going to bring a little single positive charge somewhere close to that bunch of positive charges. What is it going to sense? Is it going to be drawn toward them or pushed away by them? Pushed away, because those are like charges. That's the force exerted on it. Why is that? Because this always has an electric field around it that would be pushing away any positive charge that came close. And this senses that and gets pushed away. So here is basically the definition of an electric field. It's the force, just like we said here, electric force acting on a charge that might be brought into the area. That would indicate there's a field somewhere present. Now, if you think about this, if I extended these lines way out here, look how far they get apart. They're really close down here, but they're really far away here. That's your inverse square law. Okay? See how far apart they are? They're not very strong out there. So this is probably going to be a very small force pushing it away. But you bring that charge in closer, and it's going to be pushed away even stronger. A lot like our simple harmonic motion was, only it's a different issue here, but that's what an electric field is. It's going to either push a positive charge away or pull a positive charge toward it. That's what an electric field does. Okay? Static electricity is like that. The picture they show on page 457 shows a balloon. What they did with that balloon, I bet you, is rub it with a wool shirt or a wool cloth or something, and then put it on the wall, and it stayed there. Why? The wool put extra electrons on the balloon, and now the wall being neutral, it's attracted to that negatively charged balloon and holds it against the wall. Okay? Now, what's the relationship here? Here is the formula for electric fields. The symbol for electric field is capital E. Oh, earlier we may have used that for energy. Don't worry about that now. That means electric field. An electric field is the electric force That's the Coulomb's force, remember, divided by the Q prime, which is the charge on this test charge, I'm pretty sure. Yeah, the test charge, and this is measured in coulombs. This is measured in newtons. So electric field, 1 unit for it would be a Newton per Coulomb. Okay? A Newton per Coulomb. Later you'll run into, maybe we'll run into another name for it, but that's what it is. Okay? A Newton per Coulomb. Now, I think we've just reached our max, haven't we? Isn't our time up? Is everybody left already?
Yes.
No. Yes? Okay. All right. We'll pick up next time with example 1. Okay? Which will be the first problem we have here. So we don't have any new problems in this section. This was 17.3. No, 17.4. So we'll do example 1 here and we'll continue. Now we're making pretty good progress through 17, mostly because I don't think any of you are asking any questions. I can't hear them if you are, so I'm doing too much talking. So please participate in class. That'll slow me down a little bit. But we're making good progress. It's not going to be too long before we'll be ready for the Chapter 17 test. That'll be test 5. So be getting your other test in. Great attendance today. I think this is maybe close to the most we've had in any class, certainly in the online class, or in the, what did I call it? Virtual class. Okay. So I'm glad y'all were here. I hope you have a good weekend, and we'll see you next Wednesday. Okay?
Okay.
All right. Bye-bye. I'm going to stop the share now. Oh, I still have a few people here. Alyssa, Rachel, Deandre, Andrea, Tashandra, and Rance. I didn't even know Rance showed up. Welcome, Rance. You should have told me when you got here. Did anyone else notice anyone else coming into the class at any time? I think I got all the rest of you here already. Yeah, I got all the rest of you. But Rance, I'm glad you stayed. I never would have known you were here. Okay. Any last thoughts, questions, parting shots?
For our test, are we just supposed to email them to you, or do you have a link open in Blackboard to submit them?
Okay, now could you say that again, maybe just a little slower and maybe a little louder?
Yeah, so the test, are we supposed to submit them on Blackboard? Is there a link open for us to submit them, or do we send them through email?
Okay. The very first part, I heard something about Blackboard, but I couldn't hear what you were calling it.
Where do we submit the test?
Got it. Okay. One of two ways. Well, actually, there's a couple of ways. Let me explain that to you. Great question. Okay. You can either scan your test. Okay. Now, wait. This latest test I gave you. Now, the earlier test, if you're wanting to turn one of those in, those earlier tests, you probably almost have to scan or take a picture with a smartphone. Either one will work. Attach it to an email or go to the message thing in Blackboard and attach it to a message. Either one of those will work. Do you understand what I mean by all that?
Yes, sir.
Okay. Now, the test I just sent you, test 4, it's in Word format. I've had some students who actually type in the answers in Word and send it back to me in Word format. If you want to do that, you can, but if you don't want to do that, if all you want to do is write in your answer, then again, either scan it and send it to me as an attachment, or take a picture and send that to me as an attachment. Either the email or to the, whatever you call it, message in Blackboard. Does that answer your question?
Yes, sir.
Excellent. Any other questions? Great question. Clear these up now. All right, good deal. Well then, if there's no more questions, I think I just ended the session, but I didn't turn it off. I'm glad y'all are still here. Oh, no, I didn't end the meeting. There it is. So once I end the meeting, you won't be able to catch me anymore. Any questions? All right. We'll see you next Wednesday. Bye-bye.